see how we did with these acid-base reactions here. Okay, now these two compounds, we're doing acid-base chemistry. pKa's are given. Let's see, which one's the acid?
One on the left.
One on the left.
Yes.
Why?
pKa.
I'm personally not looking at the pKa's. I'm looking at the structures. Okay? What's the most acidic H up here? What's the most acidic H in the box?
The one on the on.
CH? OH. Okay. What's the most basic atom in the circle?
The nitrogen with the lone pair.
Okay, what's a good base? Anions or neutral nitrogens? sp3 nitrogen being most basic. Okay. These are nitro groups. Nitro is not on the functional group list for organic 1, but you will need to know nitro for organic 2. That's organic 2 functional group. They're not acidic or basic. This is your basic amine. Alkaloids, remember they all had like an sp3 nitrogen? Okay. The summary page says what? Now the only atom that's basic in the neutral state is what? Nitrogen. Yes. Here's your base. Now you do your acid-base mechanism. These electrons, let's draw that bond in there. These electrons bond to the acidic H. These electrons move on to the oxygen and become the third lone pair. The OH bond is broken and we get what? Now the oxygen has 3 lone pairs, and lo and behold, that's a minus charge, and we now have a nitrogen which has 3 ethyl groups, but now the nitrogen is bonded to what? H. Because right here, these electrons are bonding to the H. This is a simple mechanism, arrow. Don't overthink it. The arrow means it's bonding to the H. But you start, anytime you show an arrow, you say these electrons. These electrons bond to the H. These electrons in this bond move on to oxygen. Every time you move an arrow, you say what? These electrons. Ah, lo and behold, that's not a neutral nitrogen, is it? What's charged? Plus. Now we have an ion pair, a pair of ions. I'm sure somewhere, and you know from Gen Chem, that your conjugate base, acid-base pair, one's neutral, one's charged. Yeah? Learn that in Gen Chem? Okay. For example, this is your acid. Yeah, this is your base. What do you want to call this? That's the conjugate base of your acid, right? And this is your conjugate acid of your base, right? Okay. Neutral, charge. Neutral, charge. Just like any acid-base reaction, right? Gen Chem. What's new here? Other than we're doing our acid-base mechanism, which for some reason you guys don't do in Gen Chem. Do not memorize reactions. Acid-base. It's the same for this acid-base mechanism or any other million one you can dream of. Okay. How do we do on predicting those products? Questions about that? Questions about that? Did everybody get that right? Who got it right for today? Great. Those that did not get it right, no questions about any part of it? Okay. Which side is favored? Which side is favored here? Left or right? What's the acid over here? Right there. pKa of 1 is given to you. What's the acid over here? The acid is a thing that has the H. This molecule has the H here. And which molecule has the H now? Okay, there's your acidic H. Okay, so this is the acid over here. It's kind of cold. Okay, what's his pKa? pKa of 10. How do we know that? Because that's given right here. And when you give a pKa of a base, what does it refer to? Conjugate acid. That pKa actually refers to this. Okay? We don't use pKb's. We use pKa's. You got to know it refers to the conjugate acid. If the species is acting as a base. Now, if this was going to act as an acid, that would not be the pKa. And you have to clarify that. There's a comment in the summary page that maybe clarifies that. Okay, let's try another one. Down here. What's the most acidic H in the circle? Well, you got an OH and the rest are CHs. Where you want to make an anion in. We talked about how to determine which is more acidic. Okay? And you also have to keep in mind, it's everything here. Because when you do an acid-base reaction, the most acidic proton in the flask, that's going to be your acid, no matter which molecule it's on. And the most basic atom is going to be your base, no matter which it's on. You may have a molecule where the most acidic H and the most acidic base are in the same molecule. Then it's just going to self-react, and this guy ain't going to do anything. Okay, there's the acidic H. Which atom in the circle is most basic? Neutral nitrogen. What type of orbital is this lone pair in? It's in an sp2, not in a p orbital, it's sp2. It's not as basic as sp3, so it's got more s character. It's held tighter to the nucleus, but it's still basic enough to do chemistry. So, now that we've established that, then what do? These electrons do what? These electrons take the H, these electrons move on to oxygen as a third lone pair. What does that give? It's actually going to give this, okay, this is similar to that, just no nitro groups. By the way, what's the name of this compound? What functional group? It's a phenol functional group. That's actually called phenol. Okay. This is trinitrophenol, also known as picric acid. Phenols are usually have a pK about 10. This one is so acidic because of the 3 nitro groups. It's actually called picric acid because it's so acidic. You get that plus what? Please draw the other product. Right here, right? This nitrogen is now bonded to the H, right? So boom, boom, boom. Nitrogen, instead of a lone pair, the 2 electrons are now bonded to the H. And lo and behold, that nitrogen is a positive charge. There you go. Made an ion pair, also known as a salt. What's the acid over here? pK about 10. What's the acid over here? This thing has the H over here. What's its pKa?
5.
About 5. Because this thing was a base, and thus the pKa refers to the conjugate acid. So, 10 or 5, which is favored? Side with the weaker acid, this is favored by how much? 10 to 5, the difference there. Did we say which is favored in the first one?
Yes.
I don't think we said it, but this is 1. Over there we had pK of 10. Which side's favored in the first one? The right side. First one, the right side's favored. By 10 to the 9, which is, what, a billion? Billion to 1 in equilibrium. Down here, the product side is not favored. So what we can say is this is called pyridine. Is pyridine strong enough to fully deprotonate phenol? Here it's been deprotonated. The proton, the H plus is called a proton. Is pyridine strong enough to fully deprotonate phenol? Go that way.
No.
No, it will not. At equilibrium, this side is favored. What's that? 100,000 to 1. So you got 100,000 of these, and you only have one of these. I mean, that's very negligible. It's not strong enough to make it go that way. Okay, down here it's just one molecule. That's okay. We can still have acids and bases within one molecule. And that's very typical of your amino acids, which are building blocks for your proteins. Amino acid is a carboxylic acid, and on the first carbon coming off, which is called the alpha, has an amino group, NH2. Alpha amino acid. These vary by the substituent on this alpha carbon. It can be as simple as H, or it can be pretty more complex. Those are your various amino acids. But look, we have acid here, and then we have a neutral sp3 nitrogen, which is typically basic. You can get a self-reaction. Just act like these are not connected and do the same thing we did before. In terms of your mechanism, it's probably two different molecules. This may not reach over here and take the H. But in any event, can you show the product here? This lone pair is going to take on a what? Proton, the H. And this is going to give it up, okay? Let's do it two different molecules. These electrons take an H, leave that behind, okay? Now you have to envision this one taking an H. What are we going to get? This nitrogen now has how many H's bonded to it? 3. And over here, what's on this oxygen now?
3 lone pairs.
Nothing, except we left a lone pair behind. That's minus, and that's actually plus. So we have an acid and a base kind of internally here, okay, within the same molecule.
So we're going to make a dichromacy to make sure that's permeate on the two sides.
Perhaps there may be some attraction of the charges, and it may affect the conformation, which is on the next handout. Yep. Okay, which side's favored? All neutral or the two charges? Which side's favored? Well, what's the acid over here? 5. What's the acid over here?
10.
Where's the H at over here?
Nitrogen.
It's sitting on the nitrogen. This is your conjugate acid. What's its pKa? 10. Because if this is acting as a base, the pKa refers to the conjugate acid. Which is favored, 5 or 10?
10.
10 is favored. By how much?
5, 10 to the 5.
Favored by 10 to the 5. So, at neutral pH, or unless there's something else going on we haven't talked about, just okay, this molecule by itself, how does it predominantly exist? It exists in the dicharge form. Okay. Now we never show it like that because it's just cumbersome. We usually show them like this. But under neutral conditions, it exists like this because we have an acid and a base sitting right there. They're going to react. And what do we call a molecule that has two charges in it? Yeah, good. It exists as a Zwinner ion. Okay? And hopefully that one was very similar to the above, except the acid and base were just connected to the molecule. I mean, we could have connected the ones above if we wanted to by just making it one molecule. Questions about that page? Okay, how does pH play into things? How does pH? How will an acid or base primarily exist at a certain pH? You've got to keep in mind, whenever you do an acid-base chemistry, you have like an acid and then its corresponding conjugate base. Then you have a base and its corresponding conjugate acid. These are the two forms. I talked to one of you and you didn't realize that what I meant by the two forms in the acid-base reaction. Don't y'all do tons of calculations to determine which form something will exist in Gen Chem 2 and stuff? I don't know the lingo that's there, but I thought y'all did tons of calculations to determine equilibrium. Equilibrium between what? The two different forms. Okay? You need to make connections between what you know, because the lingo may be a bit different, or maybe there's not much lingo there at all. Okay. Which form will predominate at a given pH? Well, this is where the Henderson-Hasselbalch equation comes from, which is pH equals pKa plus log of B over A. What is B over A? B is the basic species. Or you can maybe, I think, call it the conjugate base. A would be the acidic species, or maybe the acid. But here's how I remember it. The acidic species is going to contain the H. The thing that has the H, if it has the H, we're going to call it the acidic species. If it don't contain the H, then it's the basic species. It's already given up the H. Or maybe it will take it back. If it takes it back, it acts as a base. So the important thing is, does it contain the H or not? It doesn't matter what the charge is. Some students say, well, it's negatively charged, so it's this. No. It depends on if it contains the acidic H or not. Okay, you can go all the way through this. In biochem, usually you derive this equation, or you used to. Equation is, well, you can derive it and see how you can come to this conclusion. Basically, we have some unknowns. If you're only missing one, then you can, well, if you have like this, this, and this, you can solve for that. Or if you have this and this, then you can solve for that. Here's a take-home. If pH is greater than pKa, the basic species will predominate. If pH is less than pKa, the acidic species will predominate. For example, look at acetic acid. How will acetic acid predominantly exist at pH of 7, which is blood pH? Will it exist as the acid or the conjugate base? Well, what is the acid and conjugate base? Here's the acid. It's the acid. It contains the H. But we know it can act as an acid and basically give up the H, or a base can take the H, and if the base takes the H, what will this become? It'll become this. You've got to know there's 3 lone pairs there, right? So there's the conjugate base. There are your 2 forms. What's the pKa? Carboxylic acid's about 5. Okay? So now we have 5 and 7. So we have boom and boom. Now we can actually solve for B over A. But I've actually already told you how to solve it right here. Let's look at our numbers. pK is 5, the pH equals 7. Which will predominate?
The base.
pH is greater than pKa, right? So the basic form will predominate. What's the basic form? Right here. At pH of 7, acetic acid will predominantly be in the ionized form. Okay? That doesn't mean it will be completely in this form. It'll be the favored form. How much will this be favored by? It's actually a difference in between your pH and your pKa. It's a difference of log of 2. Okay? It's 10 to the 2. This is favored by 10 to the 2. That means at this pH you will have, what is 10 to the 2? 100? Okay? At pH of 7, it's 100 to 1. What's that? 99% roughly? Okay? If you make the pH higher, this will predominate more and more and more. What if the pH was 5? It'd be 1 to 1. Because if pH was 5 and pKa was 5, that means log of B over A would have to equal 0. And for log of B over A equals 0, what does B over A have to equal?
No, it must equal 1.
1. See your math? Thus, we can say that if pH equals pKa, the B to A ratio is equal to 1. But if you start adjusting the pH, then you can make one favored over the other. Okay, below is just miscellaneous note. You can look at it. There's a variety of miscellaneous things because as you start doing it, a variety of things will come up. But I can't just sit here and tell you all these things. You have to figure them out for yourself and ask questions and then read. Okay? We can do some examples. There's a variety of examples in the handout. Let's look at this one. Codeine. Codeine is usually given as the hydrochloride salt, which means you react with HCl and make a salt, which is an ion pair. Well, if HCl is an acid, codeine must be acting as a base. What's the most acidic atom in codeine? Neutral nitrogen, right? Oxygen, neutral oxygens are not basic. Again, that point right there is like number 6 on the summary page. Or some number. Okay? We've already said. So this is the base. Obviously, HCl is the acid. pK of that, it's very strong acid, it's like -5. Now, no pK is given here. But guess what? It ain't going to be less than -5 because HCl is a strong acid. You can't get stronger than that strong acid. Now, its pKa is actually about 10. Okay? But you're going to react with the strong acid. These electrons make bond to H. These electrons move on to the chlorine to become the 4-form pair. And so you should be able to show that outcome, right? Nitrogen now bonded to H. Lo and behold, that's a plus charge. Chlorine has now chloride. This is an ion pair, which we also call what? A salt. That would be called the hydrochloride salt of the drug. Which side's favored? Well, that's 5. What's the pK of this? 10. That's -5. Which side's favored? 10. 10 is favored by how much? 10 to the 15. That's 100 gazillion at least. You react this with HCl, it's going to completely form the salt. Okay? Why are drugs usually given as salts? Goes back to solubility. The uncharged form is not that soluble in water. It's too many plain just carbons and CHs. Yes, it does have some polarity, but it's also got a lot of hydrocarbon. And indeed, it's not that soluble in water, which the absolute, it's hard to predict. But if we can make it ionic, shouldn't it now be more soluble in water? Yeah, and indeed it is. That's why most drugs are given there. You make the hydrochloride salt.
What's the pKa of 8?
Okay, it was up there. I said about 10. Okay. Yeah, I mean, 10 is a rough number. Usually sp3 nitrogen is roughly about 10, but it can vary. But even 8.2, so instead of 10 to the 15, it's 10 to the 13.8. I mean, it's still 100 gazillion. I think I referred to this one in last week's lab. React this one with mesylate. Mesylate comes from reacting with methane sulfonic acid. Okay? It's a sulfonic acid. Shown right here. This is very similar to like sulfuric acid on this end. This is your acid, that means this is the base. But which atom is the base? Neutral nitrogen, yeah. Well, you got which neutral nitrogen? Which nitrogen is most basic? If I answer that now. Top one where? Here? No. What type of orbital is this lone pair in? If we consider this a standard pi bond over here. Now that lone pair is in a p orbital. The sulfurs are a little bit atypical, but I would want you to think p orbital there. What do you think? All the nitrogen lone pairs are in p orbitals, except for which one? There's only one that's not. This one right here. That's the only lone pair that's not in a p orbital. It's in an sp2. Every other nitrogen lone pair is in a p orbital. Who does not understand or not at all? Any questions about that?
So let's just say the nitrogen has micromolar ketone.
Well, there's no ketone.
Oh.
There's a carbonyl. Yeah, there's a carbonyl, but that functional group is not a ketone. Functional group is a amide, or amide, or however you want to say it. Okay? Just to get that point right. Go ahead. Go ahead.
Oh, never mind. The electron would be messed up by the double bond there.
Well, I mean, this lone pair is in what type of orbital? P orbital. Because you have the carbon, oxygen, sigma bond, but then you also have the pi bond, right? There's the pi bond. There's your double bond to oxygen. And then you have this bonded to nitrogen. You see, 10 of the p orbitals are coming out actually. Over here, and it's bonded to the carbon ring. It's got a lone pair, but there's a p orbital next door. So the lone pair, we're going to put in a p orbital too. Pretend like these are all sticking straight out. Okay? Two sticking out. Well, this one can stick out, and the lone pair can interact with that one. Okay? It's hard to see there, but right? These two sticking out. But the lone pair in this one have it sticking out, and then you got 3 p orbitals overlapping. If this nitrogen was sp3, you wouldn't have that p orbital. Anytime a lone pair is next to a p orbital, it's going to want to be there. So what were you thinking otherwise? It's good that I hear your thought process. I mean, why?
I was just looking, at first I was looking for nitrogens that had 3 bonds to carbons. That was probably great.
Well, this exception, I mean, the nitrogen only has 3 bonds.
Yeah.
Like say, you think, hey, triple planar, sp2, but no, there's this major exception, which is hugely important. Anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. You've got to understand that. Okay, so once we recognize the most basic nitrogen, now we're off to, what's the most acidic H? I mean, These electrons take the H, these electrons stay behind, and you should be able to show that product. Nitrogen will take on the proton and be charged, okay, and you'll have this anion. That anion is called mesylate, and you'll have the mesylate salt. And the one over here is easier because obviously that's an acid. What's the most basic atom? It's the one in like the first or second page. There's only one basic atom in this molecule. Right here, right? We went through everything here. Questions about acid-base chemistry? Let's go back to codeine on the page over there. Codeine. Two forms are shown. How will codeine predominantly exist at blood pH, which is 7? How will codeine exist at pH of 7? Which form? The A form or the B form? Both forms are shown, right? Which form will predominate at pH of 7? Anybody have it? Is it the acidic form? Okay. Assuming that's correct, which is the acidic form? Why is it the charged form? Because it has a hydrogen, yes. Yes, it has the H. So why do you say the acidic form is going to be favored at pH of 7? pH is lower than the pKa? And you're using the summary statement of the Henderson-Hasselbalch? Another way to look at that is, yes, that's all correct. Another way to look at that is low pH acidic or basic? Acidic. Okay. If pH is low compared to the pKa, that's the acidic side. So it's going to exist in the acidic form. What if our pH was 10? Which would predominate? Well, 10 is 10 below 8.2 or above? It's above it, so that's the basic side. High pH is basic side, so the basic form will predominate. Which is the basic form? Form without the H, that form. I don't know if there's any places in the body of pH higher than 7, like the intestine. Sometimes the intestine is basic. Now this compound is going to be more soluble at lower pH when it's in the charged form. If this encountered a very basic environment in the body, it would exist more like this, which is actually the less soluble form, and maybe it would start crystallizing or precipitating or something. Okay. One word of caution about those pKa's and pHs is when you're comparing those. One of those is a constant, one of those can vary. pKa is a constant. pH can vary. Okay? You need to say the thing that can vary, where does it sit compared to the constant? I see some of you guys doing it the other way around. You're saying, hey, this one is higher than the other one, so we're on the basic side. And I'm like, no, but, okay. That one's not higher than the other one. This one's lower than that one. See what I'm saying? Make sure the thing that varies, where does it sit? Okay, other questions about pH or acid base? Any questions about upcoming lab reports that's due next week? Question?
Writing center, please. Is that familiar with laboratories?
Not specifically, and not my specific guidelines. Okay, you have specific guidelines in the lab manual. Okay. So, how useful it's going to be, it depends on what you need. How, basically how good of a writer you are and what can help you. But no, they're not going to be familiar with the guidelines for this class and for me. Okay. But they'll be quite familiar with run-on sentences and incoherent opening paragraphs and things like that. So it's a resource. Use it if it's going to be helpful. If it ain't helpful, then don't use it. Okay, guys, let's look at next topic, which is our alkanes, cycloalkanes warm-up. Unless there's other questions about acid base. Oh, by the way, IR, I think I may send out an IR question set, brief, something to work on over the holiday break. You do have problems in the workbook. I may send you something that's not in the work, the answers are not there, so you can better struggle with it. Give you an additional practice. And then next week, maybe in lab, we'll look at the answers. Use that to see the type of questions that come up and how you're doing with IR. I'll send that by email. Please look for that in the next day or so. Okay, alkanes. Here's your warm-up. Some questions there. Next was nomenclature. That was covered by video. I believe in the video I did not do this one here. I believe I did this in the video, is that right?
Yeah.
But did not do this one?
No, you did that one
That's
too.
the way I remember it. Anybody confirm that?
No, you did that one too.
I did this one in the video?
Yeah.
I did all that in the video?
Yes.
Got 2 students saying yes. I must be remembering wrong. Okay. Any questions about nomenclature? Should be nomenclature practice in your textbook. Question?
Have you arranged the order of the substitutions? If you have an alcohol or versus another side, which one would take precedence in terms of
Well, The alkane nomenclature, which is all that will be on test 1, is going to be named as an alkane. Any substituent would be named as a substituent, and they would be put in alphabetical order. For example, a OH group would be called just a hydroxy group, or hydroxyl. Okay. Show me an example of what you might be talking about, and I could give you a more detailed answer. Okay, there's no questions about nomenclature. Let's move to new stuff here. With your formulas, of course, you got to know your line bond, how many H's are there, etc. You need to be able to recognize and deal with so-called condensed formulas. Okay? For example, something that may be written like this, where it's not pure formula and it's not pure line bond complete structure. Okay? This equals this. How do we get to that point? Well, you see this CH2OH on the end. Okay? Let's start back over here with the parentheses, though. There's two methyl groups that have to be bonded to something. They're bonded to the next carbon. So I got a carbon with two methyl groups. And then this carbon is bonded to what? There's an H there, and then I have a CH2, and then I have an OH. Obviously, this H can't be bonded to two different carbons. But it can be just sort of written like that, but you have to know it's bonded here. Of course, I drew this sort of condensed, but of course this is really what? These H's are off like this, right? But in the end, this is that over there, where we have two methyls on a carbon, CH2, everybody's good with that being a CH2, OH. Okay? Now there's a variety of these. So you have to get used to this because there's a variety of ways to show compounds, and if you go out into the real world, and you got to be able to deal with it. You take an MCAT, who knows how they're going to show you the compound? You take a DAT or whatever, you know? You're out this weekend having a cool beverage and you see a structure and you're like, oh, I've never seen that look like that before. Okay? You guys on the right do this one, show a line bond structure. You guys on my left do the next one. And actually, since we're pushing time, we don't really have enough time to sit here and allow you to do that. So do these, and we'll answer those on Wednesday. Let me sort of set the stage for as we're going forward. We'll have to talk about things like primary, secondary, tertiary carbons. It's going to be no different than like a primary nitrogen. Primary nitrogen is bonded to how many carbons? One. Primary carbon is bonded to one carbon. Okay? We just need to make sure we know that. Terminology, some general reactions, which are pretty almost boring, but we just have to know what those would take place. Then we'll move into some rings. Okay? We're focusing on the alkanes. But in that, we'll look at cycloalkanes. Okay? Nothing but just hydrocarbon, alkane. And in particular, we'll focus in on cyclohexane. Cyclo, six-membered ring. Because cyclohexanes, we'll be looking at the idea of different types of isomers. We already know constitutional isomers. We'll begin talking about stereoisomers. Then we'll be moving into conformations of alkanes. And we'll be looking at drawing energy diagrams like this. We'll be looking at drawing molecules like this, circle, circle, dot, dot, which is called a Newman projection. And it's not shown here. It's probably on the blue sheet, but we'll then we'll be looking at cyclohexanes drawn in chair conformations. How to draw them, what's the terminology there, cis, trans, axial, equatorial, that type of stuff. And that will end pretty much material for test 1. Okay? Please be ready to go through this handout come Wednesday. Make use of your time. You got to do your part, right? Have a great day off. Please be safe. See some of you this afternoon over here. Okay. Have a good day, guys.